Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. What if our universe, everything we've ever observed, everything the James Webb Space Telescope has ever photographed, every galaxy, every star, every planet, every moment of human history, is just one of an infinite number of universes, each one existing simultaneously alongside ours, completely unreachable, completely undetectable, and each one governed by its own version of the laws of physics? That idea is called the multiverse. And it isn't science fiction. It emerges directly from some of the most rigorously tested, most mathematically precise theories in all of modern physics, theories that have been confirmed by experiment at a level of accuracy that no other scientific framework in history has matched. The multiverse doesn't come from imagination. It comes from the equations. And the equations, whether physicists like it or not, keep pointing in the same uncomfortable direction. Today, we're walking through the real science behind the multiverse, where it actually comes from, what different versions of it actually say, and what it would mean if any of them turned out to be true. In our next episode, we're getting into the fierce debate over whether the multiverse is genuine science or untestable speculation, and the alternative theories that try to explain the same evidence without requiring infinite parallel universes. Stick around for that one. The most scientifically mainstream version of the multiverse doesn't require any exotic new physics at all. It falls directly out of a theory called cosmic inflation, a framework developed in the early 1980s by physicist Alan Guth that was specifically designed to explain several features of our observable universe that the standard Big Bang model alone couldn't fully account for. Inflation proposes that in the very first fraction of a second after the Big Bang, we're talking timescales of 10 to the power of negative 32 seconds, the universe underwent a period of extraordinarily rapid expansion, growing by a factor of at least 10 to the power of 26 in an almost instantaneous burst. This rapid expansion naturally explains why the universe looks so uniform in temperature across its entire observable extent, why its geometry appears so flat, and why we don't see certain exotic particles that earlier versions of the Big Bang model predicted should be everywhere. Cosmic inflation is not a speculative idea at the fringes of physics. It's supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, whose detailed temperature patterns match the predictions of inflationary models with extraordinary precision. The problem, or the implication, depending on your perspective, is that the mathematics of inflation doesn't naturally stop. Once inflation starts, most versions of the theory predict that it keeps going forever in most of space, with isolated regions occasionally stopping their inflationary expansion and settling into stable universes like our own. This process, called eternal inflation, would produce an endless, continuously expanding background of inflating space, peppered with bubble universes, each one a separate, causally disconnected cosmos, forever unreachable from any other. Like, subscribe, and hype the video, because the inflationary multiverse is just the first version of this idea. The others come from completely different directions. The second major version of the multiverse comes not from cosmology, but from quantum mechanics, the branch of physics describing how matter and energy behave at the smallest scales. And it emerges from one of the most fundamental and most deeply debated puzzles in all of physics: what actually happens during a quantum measurement. In standard quantum mechanics, particles exist in superposition, in multiple possible states simultaneously, until they're measured or interact with something. At that point, the superposition appears to collapse to a single definite outcome. Physicists have argued for almost a century about what this collapse actually means and why it happens, and the question has never been fully resolved. In 1957, physicist Hugh Everett III proposed a radical answer. The wave function never actually collapses. Instead, every time a quantum measurement occurs and multiple outcomes are possible, the universe branches. All outcomes happen simultaneously, each in its own separate branch of reality. In one branch, the particle went left. In another branch, the particle went right. Both branches are equally real. Both contain observers who experience only one outcome. And this branching happens not just in physics laboratories, but in every quantum interaction everywhere in the universe, at every moment, which means the number of parallel branches is effectively infinite, constantly multiplying with every quantum event at every location in the cosmos. This interpretation, called the many worlds interpretation, is not a fringe idea. It's considered by many physicists to be the mathematically simplest interpretation of quantum mechanics. It requires adding nothing to the equations and removing nothing from them. It simply takes the mathematics at face value rather than adding a separate collapse mechanism. A 2021 survey of physicists found it among the top 2 or 3 most popular interpretations of quantum mechanics among researchers who work with quantum theory professionally. The third major version of the multiverse comes from string theory, the leading candidate for a theory that would unify quantum mechanics with general relativity, describing all fundamental forces and particles as different vibrational modes of tiny one-dimensional strings of energy. String theory is extraordinarily mathematically rich, and one of its features is that it doesn't produce a single unique set of physical laws. Instead, the equations of string theory are consistent with an enormous number of different possible configurations, different numbers of dimensions, different particle masses, different strengths of fundamental forces, each one corresponding to a different possible universe with different physical constants. The estimated number of possible string theory configurations is often cited as 10 to the power of 500, a number so large it's essentially incomprehensible. This vast collection of possible universes allowed by string theory is called the landscape. Some physicists argue that all of these possible configurations actually exist, that the universe randomly settled into one particular configuration among the enormous number of possibilities during the process of inflation or the Big Bang, and that other regions of the multiverse settled into other configurations with completely different physics. In most of those other configurations, the physical constants would be incompatible with the formation of atoms, stars, or life. But in a small subset, constants similar enough to ours would allow complexity to arise. Like, subscribe, and hype the video, because the string theory landscape has one specific controversial implication that divides physicists right down the middle. One of the most powerful motivations for taking the multiverse seriously is a problem called fine-tuning, the observation that the fundamental constants of physics appear to be set with extraordinary precision to values that allow complex structures, stars, planets, and life to exist. Vary most of these constants by even a small amount, and the universe becomes sterile. Stars can't form, atoms are unstable, or the cosmos expands too rapidly for anything to clump together. This fine-tuning is either an extraordinary coincidence, or it was designed, or it's the natural result of a vast multiverse where all possible values of the constants are realized somewhere, and we inevitably find ourselves in one of the rare universes where the constants happen to allow our existence. This last explanation is called the anthropic principle, the observation that any universe we find ourselves in must, by definition, be one capable of producing observers like us. The fine-tuning problem is one of the deepest puzzles in fundamental physics, and the multiverse provides one of the only explanations that doesn't require either pure coincidence or a designer. Whether that makes the multiverse a satisfying scientific answer or a philosophical escape hatch depends enormously on who you ask. Despite coming from completely different areas of physics, all 3 major versions of the multiverse share a common feature that makes them both intellectually compelling and scientifically frustrating. The other universes in every version are, by construction, causally disconnected from our own. We cannot travel to them, signal them, observe them, or directly detect any evidence of their existence from inside our own universe. This shared feature isn't a coincidence, it follows from the physics in each case. Bubble universes in eternal inflation are separated by expanding space that can never be crossed. Branches in many worlds can never interact after splitting. Other string theory, landscape universes are, by definition, regions with different physics that never overlap with ours. Each version of the multiverse predicts the existence of realities that are, in principle, forever beyond our ability to confirm or deny through direct observation. This is the deepest tension at the heart of multiverse physics, and it's the source of the fierce debate we'll be getting into in our next episode. So here's what the science actually produces. 3 completely independent areas of modern physics: cosmology, quantum mechanics, and string theory, each arriving at the multiverse from a completely different direction, without any of them starting with the goal of finding it. The equations simply keep pointing there, whether the physicists running them like it or not. But in our next episode, we're getting into the fierce, ongoing debate over whether the multiverse is genuine science at all, the physicists who think it's untestable speculation masquerading as theory, the alternative explanations for fine-tuning that don't require infinite parallel universes, and the deepest philosophical question the multiverse raises about what science is actually for. Stick around for that one. Like, subscribe and hype the video so you don't miss part 2, and let me know in the comments which version of the multiverse you find most compelling. I'll see you in the next one.